Hello everyone, I'm Jean Lefebvre, Associate Professor at Telecom Paris University, and I'm here to present the upcoming release of GPAC 1.0, internally called Filters. So, what is GPAC? GPAC is an open source multimedia framework distributed under the LGPL license. It's our lab's research platform, and we use it for student projects and PhD research as well. And it's mostly known for two set of tools. The first one being MP4Box and MP4 ISO-BMF packager and dash segmenter. This tool also features encoding for scene descriptions such as BIFs, laser, 3GPP teams, and it's also featuring tools for dumping and analyzing media content. And the second set of tools in the framework are media players, mostly powered by an interactive audio, video, text, and 2D, 3D graphics renderer. The renderer is scriptable through the SpiderMonkey engine for most scene description formats, and it features various network stacks and media decoders through dedicated plugins. So let's have a quick look at GPAC history. We started in 2001 the first line of codes of what will become LibIsoMedia and the player. Released in 2003 the first version of GPAC with this catchphrase, the only open source MPEG-4 systems player. And that MPEG-4 systems design actually was the reason of most of the issues we had in the architecture. We went LGPL in 2005, and since then we've been working on an ever-increasing scope of topics through EU and French-funded R&D projects. So we cover broadcasting, mobile broadcasting, datacast, digital radio, hybrid broadcast, broadband, scalable coding. We had a lot of activity on 3D, whether it's pure 3D, auto stereo displays, 360 video. We worked a lot on HEIF, we're active participants in the standardization activities there, and we worked on, obviously, interactivity for SVG, MPEG-4, and so on. After 15 years of development, we ended up in this big architectural nightmare because each of those features were added on top of the original architecture, which was not designed to be that flexible. So as you can see in the diagram, we ended up with having a common library we call libGPAC that features mostly two classes of tools. Authoring tools on one side used by MP4Box, MP4-TS, and Dashcast, and playback tools used by the players, and those tools feature the 2D, 3D interactive rendering, Dash client, network stacks, decoder plugins, and so on. But as you can see, the authoring class and the playback class tools mostly never talk to each other. So we decided it was time for a re-architecture. We wanted to get rid of all duplicated functionalities, sometimes even code, and unify the documentation and configuration which were not consistent between playback tools and authoring tools. We try not to modify the usage of MP4Box and MP4 client, so we kept the same command line interfaces. We try to avoid breaking existing APIs, and most importantly, we wanted to make sure we have the same binary results for the packages, so that you could just switch your MP4Box version but still have the same result in your processing pipeline. Obviously, we wanted also to add all user-defined media pipeline that we've been talking about, and wanted to have the many tools we had in mind for more than 10 years now. So before breaking everything, we did a bit of introspection and tried to see what we were doing in a weird way, and also check what others were doing. The most important limitations we found were usually the poor support for stream discontinuities. By that we mean switching a codec configuration, switching a codec, or even removing a codec, so going from compressed to uncompressed domain. This usually require in existing frameworks deep packet inspection to check whether a discontinuity appears in a given media frame. And most of the time, the complex cases, such as codec switch or removal, are left up to the application. And we wanted that to be completely automatic in the new architecture without requiring a pipeline flush. The other issue we found was that we were using static stream properties, such as codec width, height, and so on, but only a small subset of those properties are used for a given stream state in time. Typically, encryption might be used at some point, but then no longer used, and you still carry on encryption properties. So doing this impact also the ABI and API compatibility, because whenever you need to extend it, whether it's a user extension or because you need some new codec support, you're extending your structures, and so this impacts your ABI and API compatibility. The last problem we found was that we were using per class APIs, so typically demuxers, encoders, and so on would have their own APIs. So that simplifies the development, but at the same time it restricts the flexibility of the media pipeline, and most of the time you hand back to the application part of the graph resolution, which is kind of a problem. So that's the limitations we wanted to avoid. So the new design is inspired by data flow approaches. We have a filter session, which is a task-based scheduler that can be real-time if desired, and it manages memory garbage collection, buffer management, threading modes, mostly using lock-free queues actually, and it also handles all the dynamic graph resolution and blocking modes of filters. Each filter exposes their I/O capabilities, so that the graph resolution can be properly done. They're all single-threaded, which means that you don't need to worry about multi-threading when you design the filter. And they by default have to support dynamic stream reconfiguration. All options and documentations are embedded within the filter code, so that it's much easier to produce the documentation. And filters can load input and output filters, such as adaptive clients loading a playlist and then loading the files from that playlist. Filters communicate through data links that we call PIDs. They handle all the packet IOs and all the blocking and buffering management of each of the media PIDs. As we previously said, the properties used to describe the streams are dynamically assigned, so you can have codec types, width and height, sample rate, and so on. And they are also user assignable, so you can tag part of your filter graph with your own properties or already supported properties such as a service ID in MPEG-2. And the data is exchanged through what we call filter packets. These are reference counted processing blocks. They can be full or partial frame file, and the associated data can be either managed by the filter session, so that would be recycled memory, filter internal memory, so that's shared memory that you expose to the rest of the graph, or interface objects typically used to access GPU textures or things like that. Filters have a bunch of static properties that you commonly find in multimedia frameworks, such as timestamps, size, framing, random access indication, but all other properties are dynamically assigned, whether they are user-defined or not so common properties such as common encryption information or NTP reception timing. So the high-level impact of this rearchitecture can be summarized as follows. We introduced a new application called GPAC. Its only purpose is to let users define their own media pipelines. MP4Box has been rewritten to use filter sessions whenever possible. So that means that importers, exporters, encryption, fragmentation, dashing code has been moved to filters. The old RTP streamer from MP4Box has been removed because it only supported MP4 inputs, and we now have an RTP output filter that can consume any supported input by the framework. The players has been rewritten as well. All demuxers, decoders, and network stacks have been moved to filters. The big compositor, which is our interactive audio, video, and text and graphics renderer, has been rewritten as a filter, and the player is now mostly a filter session running at that compositor filter. All audio, video, and image export from the player has been removed, and you can now redirect through a filter session their outputs to files or whatever you want. The MP4 to TS and dashcast applications have been completely removed. They were not really well supported, hard to configure. Now you have exactly the same set of functionalities using filters and the GPAC application. So let's have a look at the new features brought by this rearchitecture. We now have a bunch of new I/O supported, such as pipes, sockets, HTTP servers, RTSP servers. We can now handle most raw formats, WAL-UV, RGB, PCM. We've been designing our own internal serialization format for distributed processing. It's compatible with all GPAC I/O, and it represents the exact state of the session. You can even encrypt it if needed. We have a much better FFmpeg support, so that means muxers, encoders, grabbers, and all the complex filters of the libav filter library are now built in. We added a TS splitter to split MPEG-2 transport stream programs in single program transport streams. And we added a bunch of tools for source concatenation, audio-video output, croppers, and so on. Another cool feature is what we call JavaScript filters. You can basically write your own filters in JavaScript. We added support for the new QuickJS engine so that we have ES 2020 support. The entire filter API is exposed in JavaScript along with the XHR, Microdom, WebGL. We added bindings for our 2D and text software rasterizer, so that means you can now do graphic overlays over WAL-UV video in zero copy mode, which is quite nice. We added support for more tools on encryption, under-file encryption and segment-based encryption. We have dual HLS and dash output using any segment format, and tools for VR, especially in HEVC, motion constraint tiling, splitting and merging, and all the tools that we had in GPAC 0.8, so AV1, VP9, ATSC3, and so on. That was also an opportunity to improve testing and coverage and making GPAC much more reliable. Previously, when we had to test a media decoding chain, most of the time we had to instantiate a player, which means creating a window, a GPU context, and very time-consuming things that would put down our virtual machines. With the new architecture, we can test most of those without even creating a window, so that means that we have now much faster testing and much more complete. So we now have 95% of the code tested. All the commits are tested. We have builds producing installers, testing the entire suite and so on, and you can check them online. Also in the process we separated the test suite, so it's now a different repository on our GitHub. We also cleaned up the documentation in this process. It's now automatically generated from the binaries, whether it's the online version, what you get in the command line help, or the man pages. We started a how-to section where we document complex use cases, how to use filters, and so on. It's a work in progress, and we obviously welcome contributions on those. And finally, we cleaned up the libgpac APIs, removed unused functions, make sure everything was properly documented. So the Doxygen is now built automatically at each commit and available on doxygen.gpac.io. So what's next? We want a final release of the 1.0 in June or July. We planned to have it earlier, but it's been a bit delayed with the recent events. We started working on automated fuzzing to check any security issues in the code. You can test the results online. And we also started working on remote session monitoring so that you can check the session status from a web browser. Our future roadmap includes support for more hardware encoders and decoders, higher level API. We actually want to work on Python integration quite soon, and we're planning to work on live ad insertion and session redundancy as well. Thank you. I hope this makes you want to try out the new features of GPAC. If you have any questions, feel free to drop me a mail or leave us a message on our GitHub pages. Thanks.